Okay, folks, mean value theorem. So we talked about the intermediate value theorem, and now related to that is the mean value theorem. Just kind of an introductory question. The calculus class has gone on a trip to explore the calculus of amusement parks. Okay, so we're going to go up to Valley Fair. The bus leaves Albertley at 8:30. It's going to arrive at Valley Fair at 10 a.m. So it's an hour and a half. If they travel a total of 90 miles, is there a point in their travel where they're traveling exactly 60 miles an hour? So if you think about this, 8 o'clock to 10:30. Whoop, sorry about that. I think I messed that up, didn't I? I think we took off at 9 o'clock, didn't we? No, 8:30 to 10. Look at that. I'm all over the place. 8:30 to 10. That's 90 minutes. And it says it's 90 miles. And so, it doesn't do much thinking here to realize that you're going, a mile a minute or 60 miles in each hour. And so that's your average speed. The question is, at some point, do you have to go exactly 60 miles per hour? Let's admit it. As we're on our way up to the trip, up to Valley Fair, the fact is that there's going to be a lot of times that we're going 70 miles per hour. And, there's going to be times where we're starting and stopping. And so, we're going to start down at 0 miles per hour, I'm sure, as well. But does there have to be a time where we're going exactly 60? Yes, there does. The next question says, is there a time when we must be going exactly 55? Well, if you take into consideration that the vehicle is going to have to start at 0 miles per hour and eventually get up to that 60, it would make sense that you would have to cross 55. We would say that this is continuous. You have to cover every value in order to get to that 60. But now here's a little bit more challenging of a question. We'll let you think about this. Is there a time where I have to be going 65 miles per hour? Huh. I don't know. I mean, the average rate of change is 60. I mean, maybe we could reason that if we started 0 miles per hour, maybe we'd have to get to 61 or 62. But would we have to get to 65? The fact is there's nothing that suggests we would have to get to 65. There really isn't. Well, the fact is that, 60 miles an hour, that's our average rate of change. And so we know that that's the speed that we have to cover at some point. And this brings up this idea of what's called the mean value theorem. And the mean value theorem, the graphical representation is very simple. What it says is this. Suppose you have a function that starts, say, here and ends, say, here. And it, looks like that. We'll call it function f. Then the average rate of change, we would say, would be this red line. Is there a spot on that function where the derivative is the same slope as that red line? And if we just pick a few points here, say we pick this spot right here, if you were to draw a tangent line, you would say, well, no, those slopes are not the same. If you pick a spot here, you would say, well, nope, the red and the green definitely are not the same. But if you kind of glance here, maybe about that spot, you'd say, oh yeah, the slope of the red line and the blue line are the same. So there is this spot here. And so the mean value theorem says this. Sorry, I actually mixed these two up, graphical, and then we'll say let f be continuous and differentiable. So differentiable and continuous means it's nice behaving. Doesn't have any corners, doesn't have any jumps in it. Very nice, gentle curve. Okay, let f be continuous and differentiable over the interval AB. Okay, so we have A here, and we have B here. Then there exists C in the interval AB. So C that sits somewhere in between AB, such that the derivative at C, so f prime of C, is equal to the average rate of change of the function. An average rate of change is just a fancy way of saying slope. So what would be the slope of that red line? It would be f of b minus f of a over b minus a. So this is referred to as the conclusion of the mean value theorem, which we make use of in some of our problems. So you have some application in our trip to Valley Fair. You have a graphical representation, and you have the language. So consider the functions below. Estimate a value c in a given interval that satisfies the mean value theorem. So I'm going to go ahead and draw a function here. Okay. And we are simply going to connect these two dots to say that that is the average rate of change. So you should be able to look at that now and pick out a spot where you think that if I were to take the derivative at that point, I would get a slope that would be the same as the red line. And I don't think it's anywhere here, but I would say that it's probably somewhere right about there, you know, if you draw a tangent line there. But if you notice, it looks like there's probably also one right about, right about there as well. So I would say that, at about that spot, so at about -3.5 and about, say, 5, that would satisfy the mean value theorem. And then we're going to do another one here. Pick a spot there, and we're going to pick a spot there. Okay, and it'll look like that. And as you notice here, if we connect those two, you want to say, when is it that we have a slope that's the same as that? And if you look here, you can't find a spot where that's the slope. You really can't. As you think about that, you're wondering, why can't we find a slope like that? Well, that's because the mean value theorem does not apply in this situation. Why? Because it's not differentiable there. That's a corner. So your graph must be nice behaving. If it has a corner or it's discontinuous, then it does not apply. So we're going to kind of bring this into play with a couple examples. Use the mean value theorem to find the equations for lines tangent to the curve that have slopes equal to the average rate of change of the function over a given interval. Confirm your answer by graphing the function, the tangent lines, provide a sketch. So we're going to use the conclusion of the mean value theorem here to find these equations for these tangent lines. F prime of C is equal to f of B minus f of A over B minus A. And what I'm going to do right now is I'm going to focus on the right-hand side. I can get a really good picture of this, okay? I'm going to go in and I'm going to type in negative x squared and then minus 6x. And we are going to evaluate that at 1 and at -4. Make sure you do the order correctly so you don't mess it up. So we have f of 1 is equal to -7, and f of -4 is equal to 8. So therefore, if I do f of b, that would be -7 minus f of a would be 8, divided by, so this is a and this is b, so b would be 1 minus -4. So I get -15 over 5, which is -3. So -3 is is that right side. So equals -3, okay? And that's the average rate of change of the function. I'm actually going to graph the function so you can see. Okay, we see what the function looks like, but I just want to look at it from -4 to 1. So see if we can do this. I tried doing this earlier. If you can restrict the domain by just simply doing this. Press a divided sign and a parenthesis, and then we're going to say x must be greater than or equal to. I do second math to grab the test area, and that'll be number 4, greater than -4. And I do second catalog, and I grab the and command. Then x must be, so x, and we're going to go second test, less than or equal to number 6, less than or equal to 1. And now we're going to look at that graph. So there we have it. So we get this kind of sketch. Okay. So does that look like an average rate of change of -3? And I would say, sure, yeah, that looks like a pretty good representation. So that's what we just determined, that the average rate of change over that interval is -3. Now we're going to set that equal to f prime of c. So that means we need to find this derivative, which is -2x minus 6. We want to find what x is. That will be our c value. -2x is equal to +3 when we add that, so x is -3/2. Now, as you look at this, if I press trace, if I go to -3/2 or -1.5, so about right there, does that look like it could be a spot where the derivative is -3? Well, sure. Does -3 fall within this interval here? Yes, it does. The mean value theorem said it would. So here's what I have. I have to determine slope and a point on the line. The slope is -3/2. The point on the line, well, I'm sorry. The point is -3/2. The slope is this guy. That was the slope. We said the average rate of change and the slope is -3. To figure out my y value, I can go to my table and I type in that -3/2, and I get 6.75. So y minus 6.75 is equal to -3 times -3 over, sorry, I'm struggling today, times x plus 3 over 2. So y minus 6.75 is equal to -3x. -3 times 3/2 is -9 over 2. If I add that 6.75, we have -9 divided by 2 plus 6.75, and I get 2.25. So y is equal to -3x. That's plus 2.25. So I'm gonna graph that line. -3x plus 2.25. And look, the graph that I get, that line has the same slope and is tangent to the original function. That's what we've just shown. Okay? So let's try the next one here. First, notice that this function is discontinuous at x equals -3, and that does not fall in the interval. So we're okay to use the mean value theorem here. If the interval instead of -2 said -5 to 4, we would say the mean value theorem does not apply. So let's do f of b and f of a. So I go ahead to my calculator. One of my y equals, we'll get rid of these pieces here. And we'll do 2 divided by parentheses x plus 3. And we're going to go into our table. And we're going to type in 4. So f of 4 is 2.8571 or 0.28571. And then f of a, if we type in -2, we get 2. So as we set up f prime of c is equal to f of b minus f of a divided by b minus a. We have f prime of c is equal to 0.28571 minus 2 divided by 4 minus negative 2. Let's see what we get here. 0.28571 minus 2 divided by 6, and I get negative 0.2857. Very good. So that's f prime of c, or that, I'm sorry, that's yep, that's the derivative at that spot, the average rate of change. If we go into y equals, and I want to view that over that specific domain, I can go divided by parentheses. We're going to say x is greater than negative 2. So I go into my test, grab number 4, greater than or equal to negative 2, and go second catalog, and grab the and function. And then x is second test, less than or equal to number 6, less than or equal to negative 2. 4, excuse me. We'll check out that graph. And there it is, okay? So that graph, you can see it looks just like that. Does that look like it has an average rate of change of negative 0.2857? I would say it does. So what do we need to do now? We need to find f prime of c. We need to find the derivative of that. I'm going to go ahead and use the chain rule. I've got 2u to the negative 1, because I'm going to write this as 2 times x plus 3 to the negative 1 power. The derivative is negative 2u to the negative 2, or negative 2 over u squared. And I have x plus 3 here, and the derivative is 1. So the derivative is negative 2 over x plus 3 quantity squared. I'm going to set that equal to negative 0.2857 over 1. I'm going to cross multiply. I get negative 2 is equal to negative 0.2857 times x plus 3 quantity squared. I'll take the negative 2 and divide it by negative 0.2857, and I get 7 is equal to x plus 3 quantity squared. Take the square root of 7. I have plus or minus 2.64 is equal to x plus 3. And I subtract 3. So negative 3 plus or minus 2.64 is equal to x. Let's find out what those are. We have negative 3 plus 2.64. I get negative 0.36. And I get negative 3 minus 2.64. And I get negative 5.64. Well, which one of these falls in the interval? And if your answer was negative 0.36, you're right. See, our slope is negative 0.2857, but our point, we found that our x value is negative 0.36. Negative 0.36 is our x value. It falls in that interval. The negative 5 does not. So that's what we use. If I go to my table and I type in that negative 0.36, I get 0.757. So I'm going to finish this off here by writing an equation for a tangent line. Y minus 0.757 is equal to negative 0.2857 times x plus 0.36. If we take negative 0.2857 and we multiply it by 0.36 and we add to it 0.757, you can see we get 0.654. Now, why did I want to do that? So I could go into my y equals here. I could type in negative 0.2857x plus 0.654. And if you look at that graph, Yeah, it touches tangent. Not only does it touch tangent, it has the same slope as that secant line. So you don't have to graph it on your calculator. I just want you guys to understand what the heck it is we're doing, because there's a lot to keep track of here, like f of b and f of a, and then what is f prime of c? Well, that's your slope. When you actually find c, what is it? Well, c ends up being your x value that you use for your point on your line. A lot of people don't know what these things mean, and that's why you're trying to see the problem all the way through. So sorry if it's a little confusing there. We'll take some time and look at it together as well. But let's look at an easier example, okay? Kind of left the tougher ones. Let's look at the easier one. It says, consider the following tables. Let f be continuous and differentiable over the entire interval. So look at what's happening here. We start -2 and we go to 1 and 3. And look what happens to the function. It goes from 9 to 16. So it goes up 7 there. And it looks like it goes down 17 then, okay? So the function goes up and then it goes down. It says, does there have to be a value c in the interval from -2 to 3 such that the derivative is -2? Well, what that means is there f prime of c that satisfies f of b minus f of a over b minus a? So is there a time where the slope has to be -2? Well, let's look at the change over the entire interval. Let's look at f of 3 minus f of -2 over 3 minus -2. Okay, let's see what we get. F of 3 is -1 minus f of -2 is 9 divided by 3 minus -2, and you get -10 over 5, which is -2. So yes, there is, because f of 3 minus f of -2 over 3 minus -2 is equal to -2. So the mean value theorem guarantees that there's going to be a spot where the derivative is exactly -2. It says, does there have to be value c in the interval -2 to 3 such that f prime of c is 7 over 3? Well, if you look right away, what we did right away is you look at, it goes up by 7 here, and this goes up by 3 here. So you can see the slope is 3. So again, f of 1 minus f of -2 over 1 minus -2 is, well, f of 1 is 16 minus f of 2, or -2 is 9, divided by 1 minus -2. So I get 7 over 3. So yes, mean value theorem guarantees. Let's look at this. Does there have to be a value c in the interval -2 to 3? Oh, should say 0 to 2, sorry. Such that the derivative is equal to 5. Yep, I see it goes up 5 there and goes up 1 there. So slope is 5. So f of 1 minus f of 0 divided by 1 minus 0 is 3 minus -2 over 1 minus 0, which is 5 over 1. Yes. Mean value theorem guarantees. Is there ever a time where the derivative has to be, so again, we're going to go from 0 to 2, sorry about that. Is there a time where the derivative has to be 0? Huh. Well, here I went up 5. Here I went up 2 or 3. Altogether, I went up 8. No. No, the mean value theorem does not guarantee. We can't find any interval where the slope is 0. If this would have been a 3 here, then we would say, oh yeah, that last part we just went up 0 there. So that would have worked out. But there's no spot where that happens. So therefore, the mean value theorem does not guarantee something. All right, there we go. 25 minutes on the dot.